here's a beautiful number theory challenge that I'm excited to share with you. It's a statement that if n greater than 1, prove that 1 factorial squared plus 2 factorial squared plus 3 factorial squared all the way up to n factorial squared is not a perfect square. And I'm going to show you two approaches. The first is going to be pretty accessible and intuitive to as many people as possible. The second is a refinement of the first approach, and it's going to be a creative, fast trick. And then finally at the end, I'm going to explain how you think about these problems and how you even come up with these approaches. Okay, I'm going to give you a higher level look at these problems. So let's start off by understanding how we approach this kind of question. And I'd love for you to drop a comment down below if you have any thoughts or your own solution to this problem. So what we're going to do is we want to show this is not a perfect square. Let's try to actually understand it. Okay, I'm just going to show you the thinking process. So 1 factorial squared, if you're just going to look at 1 factorial squared, that's of course 1. Okay, so 1 factorial is 1. Then we're going to look at 1 factorial squared plus 2 factorial squared, and very quickly we're going to see something interesting. Okay, we'll get to that. 1 factorial squared plus 2 factorial squared is 1 squared plus 2 squared, which is 5. Okay, so here we have 1, and then you can keep going. So we have 1 factorial squared plus 2 factorial squared plus 3 factorial squared. That's going to equal to 5 plus 3 factorial squared. 3 factorial is 6, so 6 squared is 36, so we're going to get 41. So far you see they aren't perfect squares, okay? So you're getting a pattern. I mean, you first have to actually understand what's going on. Then we go 1 factorial squared plus all the way up to 4 factorial squared, dot, 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 plus 4 factorial squared. And now that's going to be 41 plus 4 factorial squared. 4 factorial is 24, squared you get 576. 576 plus 41 is going to be 617. Okay, so we get 617. So things are getting a bit crazy, right? But they're not perfect squares. You know, 626 is the closest, 625 is the closest perfect square here. So how do we actually like prove something out of this? Now here's what's going to get interesting is that once we get, and this is going to be an intuitive explanation, once we keep adding higher numbers, okay, 5 factorial squared, 6 factorial squared, the unit digit is always going to be 0. This is going to be super interesting. Okay, because I'm just going to not even add it up. I'm just going to show you 5 factorial squared, right, is 5 factorial has 5 times 2 in it. So we can write this as 4 times 3 squared times 5 times 2 squared. And 5 times 2 is 10. So it's 10 squared. Now you see that any number times 10 squared, you know, just adding 2 zeros to it, right, whatever the number is. So what you see there is that basically the units digit of this, it doesn't matter what it is, okay, we're not going to be able to calculate this eventually. The units digit is going to be 0. And that actually persists for any n. Okay, even if I do 6 factorial squared, 6 factorial is going to have a 5 times 2 in it. 6 times 5 times 4 times 3 times 2 times 1. So even you don't need to square it. It's going to be divisible by 10, so its unit digit is going to be 0. Now I'm going to abstract that on this side of the board. So what I'm going to do is I'm just going to show you that n factorial squared, or even n factorial itself, is divisible by 10 for n greater than or equal to 5. Okay, so that's our first observation. What does that mean? That means that the units digit of n factorial squared plus n minus 1 factorial squared all the way up to 3 factorial squared plus 2 factorial squared plus 1 factorial squared, which is this expression here, the units digit is always going to be 7 as long as n is going to be greater than or equal to 4. Okay, why is that? Because every time we're just adding on a number whose units digit is 0 because it's divisible by 10. So just think about addition, it's going to have a units digit of 7 for n greater than or equal to 4. Okay, so therefore n greater than or equal to 4 implies that 1 factorial squared plus dot 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 plus n factorial squared, okay, has a units digit of 7. Now that's pretty cool. Why do I bring that up? These are the kinds of patterns you have to see in math. That's why math is so beautiful, because when you try to show this is not a perfect square, what you're thinking about is what is a property that perfect squares satisfy that this number does not satisfy. If there is such a property, there should be one. That's how you're going to solve this problem, because you can't possibly enumerate them all. And what's interesting is that perfect squares, what's their unit digit? Okay, let's just think about what their units digit is. So I'm just going to actually erase this from the board. All right, so what's the units digit of a perfect square? So it's interesting if you think about how multiplication works. Basically, if you have any number, the units digit of its square is just the square of its units digit, the units digit of that. Okay, so let me actually just make that clear in one step. So if you have a number like, for example, 27, right, and you take its square, how does this work, right? How does carry multiplication work? 27 times 27, you're going to take 7 times 27, which is going to be 9, and then the 4 is going to get carried. 7 times 4 is 14, you're going to have an 18. So you're going to have a 189 there, right? And then what you're going to do is you're going to say 2 times 7, right? But here your 2 is actually 20. So you have to actually put the number here. So 2 times 7 is going to be 4, then you carry a 1, and then you have 2 times 2 is 4, which is then you add a 1 is 5, and so you have a 0 here. So notice what happens here. The units digit of 27 squared was just the units digit of 7 squared, right? The units digit of 7 squared was 49. That's all that mattered. So if you think about it that way, that's just an intuitive way for everyone. Okay, I'm going to give you a rigorous proof when I get to the next method I'll show you. But that shows that if you take a number and you want to find the units digit of its square, you just have to square its units digit, which is pretty easy. Because now what we know is what are the possible units digits of perfect squares. We'll just square 1 through 2, 3, 4 up to 9 and see what their units digits are. Alright, so 1 squared, the units digit is 1. 2 squared, the units digit is 4. 3 squared, the units digit is 9. So far so good. 4 squared, the units digit is 6, so you get 16. 5 squared, the units digit is 5, so you get 25. So far we've seen 14965. What's interesting? We're going to cycle now. So you get to 6 squared. 6 squared is 36, so we see a units digit of 6. Okay, we've already seen that. 7 squared is a units digit of 9, so we see 49. We've seen that. 8 squared is 64. We've seen 4. 9 squared is 81. We've seen 1. And then you don't need to do 10 squared. You know the units digit is 0, or you can do that anyway. So 10 squared, the units digit is going to be 0, so it's going to be 100. Okay, so 10 squared is not 0, but 10 times 10 is 100. So you see that the possible units digit of any perfect square is going to be 1, 4, 9, 6, 5, 6, 9. Now repeating 1, 0. So none of those include 7. So therefore, this cannot be a perfect square. Now, I haven't actually given you a super rigorous proof. I want you to try to make it into a rigorous proof, but I'm going to give you a rigorous proof now using a slightly different approach, which is a bit more nicer. Okay, instead of looking at the units digit, which is the remainder when you divide by 10, I'm going to show you that is what is modular arithmetic modulo 10. That's what we've done basically. Let's instead look at modular arithmetic modulo 3, which is dividing by 3. And it's going to be super slick and beautiful, and I'm just going to show it to you right now. So let's look at dividing by 3. Let's look at modulo 3. Okay, so this is a bit more of an advanced method, but we're just taking remainders when you divide by 3. So here what's interesting is that 1 factorial squared is 1. So its remainder when you divide by 3 is 1, right? 2 factorial squared plus 1 factorial squared, so I'm just writing it in reverse order, is going to equal to 5. We've seen that. So its remainder when you divide by 3 is 2. Okay, so this is going to be interesting. Now, once you add on the 3 factorial squared plus 2 factorial squared plus 1 factorial squared, its remainder when you divide by 3 is going to be the same as the remainder when you divide 2 factorial plus 1 factorial squares, adding up their squares by 3, because this number is divisible by 3. Of course, it's 3 factorial, and any n factorial for n greater than 3 is going to be divisible by 3, because you've got to multiply with 3 to get the n factorial. So it doesn't matter what this is, okay? You can find this, it's 41, but its remainder when you divide by 3 is the same as the remainder when you divide this by 3. And this is modular arithmetic. So what we write to make this very concise is we say that, I'm going to write it as follows: 1 factorial squared plus 2 factorial squared plus 3 factorial squared plus ... plus n factorial squared. The way people write this is it's congruent to 1 factorial squared plus 2 factorial squared modulo 3. What does that mean? That basically means the remainder when you divide that expression by 3 is the same as just the remainder when you divide 1 factorial squared plus 2 factorial squared by 3. Why is that? Because all these terms, 3 factorial squared all the way up to n factorial squared, are all divisible by 3. Okay, so therefore their remainder when you divide by 3 is just 0. So all you have to do is find the remainder of this when you divide by 3, which we know is 2. Okay, and here's the interesting thing. So I've got that. Okay, the remainder when you divide this expression by 3 is always 2, except at the very first one. And that, of course, is a perfect square. Okay, so you can't say anything there. But because of this, now we're going to observe something beautiful about perfect squares. Just like a perfect square couldn't have a units digit that was equal to 7, a perfect square cannot have a remainder of 2 when you divide by 3. Why is that? because all you have to do, it's the same principle as with the units digit of perfect squares that we saw, is that if you look at 0 squared modulo 3, the remainder when you divide by 3 is of course 0, right? What that tells you, what this statement tells you mathematically, is that the remainder of any number divisible by 3. So if it's divisible by 3, it's congruent to 0 mod 3. Its remainder when you divide by 3 is 0. You square it, it's still going to be divisible by 3. So this is what this statement is saying, that a number whose remainder is 0 when divided by 3, its square is also going to have remainder 0 when you divide by 3. This is why modular arithmetic is so natural. And then you have 1 squared is also congruent to 1 mod 3. Same idea, that if you take a number whose remainder is 1 when you divide by 3 and you square it, its remainder is still going to be 1 when you divide by 3. And I'm just going to briefly explain that here. The reason for that is if you take a number whose remainder is 1 when you divide by 3, it's a number of the form 3x plus 1. And if you square it, you're going to get, by the binomial theorem, 9x squared plus 6x plus 1. And you know here that these two expressions are, this is going to be divisible by 3 because it's equal to 3 times 3x squared plus 2x. And then you're going to add 1. So you can see it's remainder of the square of something whose remainder when you divide by 3 is 1. You square it, its remainder when you divide by 3 is again 1. So this is what we're saying here. And then finally, the only other possible remainder when you divide by 3 is 2. And then you're going to get 2 squared is going to be 4, whose remainder when you divide by 3 is 1. So you're going to get 2 squared is also what we call congruent to 1 mod 3. I encourage you to write out the same expression, 3x plus 2 squared. And to see that if you take a number whose remainder when you divide by 3 is 2 and you square it, its remainder when you divide by 3 is going to be 1. So these are all the possible remainders of perfect squares when you divide by 3. And so therefore 2 is not included. So that completes the proof. You just have to check that for n equals to 1, which we know in that situation that it is a perfect square. Otherwise, it's fine. I hope you loved that video, and if you enjoyed the video, please leave a like. It makes a huge difference to the YouTube algorithm. It really encourages this video to be recommended to as many different people as possible. It means a lot that you've watched so far. Also, please hit the subscribe button if you want to see lots more fun math content. I do math across all levels and topics, and I really love sharing math knowledge. I'm a research mathematician. I love doing this in my own time and sharing as much math knowledge as possible. I also want to give a huge thank you so much to Alex, Nathan, and Trang for their ongoing support on Patreon, and Enehota and AJR for their ongoing support as a YouTube channel member. The support on Patreon and YouTube makes a huge difference to the channel. Small contributions there really add up. I currently do everything on my own. I put all my free time into doing YouTube content, which is almost a full-time job. Plus, I love to pay for everything on my own, all the equipment, because I really love helping people, but small amounts of support there really help me free up time to outsource work like editing work, and to really ramp up production and create tons of math content to really change lives through math education across all levels. And so I'm super grateful for all the support there, plus the exclusive perks on Patreon, including a members-only Discord server where you can chat math with me and other members, exclusive news and updates about my channel in advance, well wishes, holiday greetings, personalized thank you message, and my gratitude, because as I keep producing math content, I always remember everyone who supported from the beginning, including people who watched the videos, liked them, commented down below. That all makes a huge difference. So if you want to support, check out the link in the description down below. It makes a huge difference. I'm going to recommend to you another video that you're going to love. It's going to be 2 videos. The first one is going to be a proof that the number 1 plus half plus 1/3 all the way up to 1 over n is never an integer for any n. It's a really popular video on my channel. You're going to love it. Check it out here. It's another really fun math proof. And here's another video you're going to love. It's basically a solution of the Pythagorean equation. What are the possible integer side lengths of a right triangle? And it actually introduces the subject of arithmetic geometry, which is graduate level math. It explains it in a very nice way in this video. You're going to love that. Wish you all the best, and I'm super excited to catch you in the next video.